Hi there. Welcome to Lecture 8 of Machine Learning from Data. We're going to be talking about linear models, specifically linear classification and linear regression. Okay, now, we've spent a lot of time and energy, on some theory, and large amount of that theory was to establish the first step in machine learning, which is that E-in can be made close to E-out. Okay, and we studied this approximation versus generalization trade-off. Okay, and that's absolutely fundamental. It's always there, and you have to ensure the first step of learning. And today, we'll spend a little bit of time sort of addressing the E-in close to zero issue, because if you spend all this time and theoretical energy establishing E-in is close to E-out, but you don't manage to get E-in close to zero, then it's all for naught. Okay, so we need both. Okay? And today we'll spend a little bit of time discussing the E-in issue, E-in close to zero issue, specifically in the context of linear models. It's a very powerful model. Okay, so let's just recap. Okay, so where we were up until the last lecture. So we've sort of finished this theoretical tour de force where we developed this VC theory that applies to infinite hypothesis sets and establishes the link from E-in to E-out. So E-out is at most E-in plus a complexity error bar omega of dVc. So there's this VC dimension that summarizes, that captures the complexity of a hypothesis set with respect to its ability to fit data. Okay, basically, and in this formula is embedded the sort of approximation generalization trade-off, which is, E-in is how well did you fit your data, and you'd like a large hypothesis set, a large VC dimension in order to ensure fitting the data well. But then how confident are you that E-in will generalize to E-out? You'd like a small hypothesis set, a small VC dimension. And that's summarized in this curve here, where if we plot on the x-axis the VC dimension, the in-sample error will gradually be dropping as you increase the complexity of a hypothesis set, as you increase its VC dimension, and that's because I get to pick the hypothesis G from my hypothesis set. So if you give me more options, I'll be able to fit the data more easily and get a lower in-sample error. Okay, but as you increase the VC dimension, this omega of the dVc is increasing, and so the bound on E-out will typically have this U-shaped behavior, and that sort of implies that there's this optimal VC dimension, dVc star, and that sort of sets a fence around what you can do in order to establish that E-in is close to E-out. So you want to use a hypothesis set of this VC dimension, this complexity. And then the question becomes, well, how to choose? There may be many hypothesis sets with that complexity, so how to choose one? And that's a lot of the effort that machine learning expert has to bring to the table, which is to understand that you can't just use as big a hypothesis set as you want. The size of this hypothesis set dVc star will depend on the number of data points that you have available. And based on that number of data points, we have a complexity. Now there are many choices with that complexity. Which one should I choose? Okay, and we'll just discuss a little bit of that today. Okay. Now, on the other side, we discussed another view of this trade-off, which is the bias variance analysis, which is also a breakdown of the out-of-sample error into two terms, the bias and the variance, and therein lies this approximation generalization trade-off. Okay. And the bias variance analysis is able to take into account the algorithm that picks the final hypothesis, but it only applies to the squared error. And it breaks down the out-of-sample error into two terms, just like the VC analysis. It says that your out-of-sample error is, the sum of two terms, the bias, which roughly speaking corresponds to how well can you fit the data, as opposed to the VC E-in, which is how well did you fit the data. Okay, so the bias is how well can you fit the data, and as you have a larger and larger hypothesis set, as we have a larger and larger VC dimension, your capability for fitting the data, i.e. your ability to approximate the target function, increases. So it's similar to how the in-sample error behaves when you increase your hypothesis set complexity. Okay, so we would like a large hypothesis set if we want to get the bias small, but unfortunately, as you do that, as you use a larger and larger hypothesis set, there's this best hypothesis in there, but when you generate a finite data set, you can't find it. You output something around that, because with one data set, and with another you might output something else, and so on and so forth. So there's this variance around that best you can do that, comes from the randomness in the data set. And the larger the data set, the less that randomness. Okay, so this variance term also comes in. And now, the smaller the hypothesis set, the smaller the variance will be. And the out-of-sample error is the sum of these two, and there's the trade-off. You want to get both the bias and the variance small, which means you want to choose a large hypothesis set to get the bias small and a small hypothesis set to get the variance small, and there's the trade-off. Okay, and we saw that in an explicit concrete case of learning this blue target function with flat lines or lines with slope. Okay, the flat lines, slightly simpler hypothesis set, more constrained, less able to fit the target function, and so therefore the bias is large. Okay, but by virtue of that constraint, by virtue of being simple, the variance is small. There's not much variability in what's output, and when you look at the bias plus the variance, it's whatever it is, 0.75 in this case. Okay, the more complex hypothesis set with sloped lines. Look at the wildness. This is coming because when you generate two data sets, a data set of 2 points, almost anything can happen, and you get sort of a wild-looking array of lines. Okay. But on average, you will get this red line, and on average it fits better than the flat line, but the variance is huge, as indicated by this gray region. Okay? And so when you add up the bias and variance, because that's a theorem, the expected out-of-sample error is the bias plus the variance. When you add those two up, you find that the simpler hypothesis set wins by virtue of having much smaller variance, even though its bias is high. Now, if you increase the number of data points, okay, that tends to control the variance. Okay? And if you increase the number of data points, then the slightly more complex hypothesis set in this example wins. If you had 5 data points, the slightly more complex line with slope wins by virtue of the fact that it maintains approximately the same bias, okay, but its variance shrinks a lot, and then the bias plus variance beats the bias plus variance for the flat lines. Okay. Now, I want to come back to the theory, before we move on, and let's revisit the VC theory, because I want to first tell you how general it was. I mean, that was just, any target function, any hypothesis set, any algorithm that picks a hypothesis from the hypothesis set as your final hypothesis G, and any input distribution P of X that's generating the data. Okay, so it's completely general. It applies to any machine learning problem. Okay, and you can, in principle, get this link from E in to E out for any machine learning problem. That's fantastic. But, so this is a warranty. This bound that links E into E out is a warranty, and this warranty has certain conditions for not being void. You will void this warranty if you violate those conditions. And what are those conditions? They're simple conditions, okay, but believe me, people always violate these conditions, even though they're simple conditions. Okay, so what's the first condition? Okay, you cannot look at your data before you choose your hypothesis set. Okay, it's a very simple condition. Okay, and it looks very constraining, but a long time ago we said it's without loss of generality, but it has to be fixed ahead of time. And then now that we have this trade-off, we see, okay, that since you have to fix it ahead of time, that introduces the possibility of failure. It's possible that now you fixed it ahead of time and you managed to get E in close to E out, and the E in was large. You failed. Okay. So this notion that you have to fix the hypothesis set before you look at the data introduces the possibility of failure. That's fundamental. You can only learn if it's possible to fail. Okay. Now, that condition is violated all the time, and people are misapplying the VC analysis, thinking that, I only need to apply it when I use the big hypothesis set. But if you're going to, use the following kind of workflow, let me try a simple hypothesis set. Oh, it succeeded. Fantastic. I'm done. I can use the VC analysis, blah, blah, blah. Oh, but it failed. Now let me try the more complex hypothesis, and that succeeded. Oh, well, I know that I have to apply the big VC dimension. Okay, that's true. You have to apply the big VC dimension whenever you try a more complex hypothesis set, but you have to apply that big VC dimension also for the case where the simple hypothesis set succeeded. So it doesn't matter whether you search your ultimate huge hypothesis set sequentially or all at once. It's the same bound. Okay? The bound is sort of giving you a safety net. It's controlling the probability that you will be in trouble for the entire process that you are implementing, the entire process up to the stopping condition when you say fail. Okay. The data must be generated IID. Okay. Now, you need that in order to apply the Hufting bound that allows you to conclude that E out is close to E in. Okay. It's essentially something like a law of large numbers. Okay. That's usually not so hard to abide by. So your data is coming from some, data generating process, and each data point is coming to you IID. Usually not hard. What's hard is to ensure that the data and the test point that you're going to be tested on come from the same P of X, the same bin, essentially. So we sort of phrased this long time ago by saying that if you take a sample of marbles from a bin, look at the fraction of red in the sample, you can only say something about the fraction of red in that same bin. You don't poll in Australia and try to predict the election in the USA. Okay? And those are the same issues that are at stake here when you're looking at generating your test point. So it must be the case that your data is generated from the same distribution that your test point is coming from. And we may ask, what happens if these assumptions, these conditions are violated? Does it mean that, the VC analysis is approximately true if I approximately violate these conditions? Anything can happen. That's the Wild West now. Okay. There's no almost violating these conditions and an almost void VC warranty on E out. There's no such thing like that. If you violate the fact that the training data are not coming from your test distribution, we have no idea, what's going to happen to your E out. And it's just like saying, does polling in Australia give me some idea about what's going on in the election in the USA? Probably not. Okay, it's a totally different, can of people. Okay, so you cannot violate these assumptions. If you violate these assumptions, you will pay the price, and that price can be huge. And later on in this course, we will see examples of when these assumptions are violated, and we're done. Okay, so that's the theory of approximation and generalization. There are a number of conditions, best practices or essential practices for how you generate the data and how you sort of approach generating the final hypothesis. You must satisfy those. Now let's move on to the linear model. Let's talk a little bit about how we get E in small, in particular linear models. So we're going to study the linear model in the context of three types of learning problems, not specifically related to the linear model per se. They are sort of general types of machine learning problems, and we'll illustrate these problems for the credit application. Okay, so you're doing credit analysis. Okay, and your client says, just tell me approve or not. Should I give the guy credit or not? Okay, so that's one kind of problem. Let's call that approve or reject. Okay. And another kind of problem that the client might say is, don't tell me approve or not, just tell me the credit level. How much credit should I extend? Okay, so credit level. Credit level. Okay, so that's a different kind of problem. Okay, different from approve or not, and we'll see what exactly is the difference. And then one final type of problem is, the client says, don't tell me what to do. You just give me a probability. So were I to, let's say, give this guy credit, what are the chances they will default? Okay, so the client is asking for a probability of, let's say, default. And you can see these are sort of three distinct types of problems in that the client is asking you to sort of give them different types of information about the input object, in this case an applicant. Okay, now we call this approval reject, and that's what we have focused on so far, classification. Okay, so this is classification. Okay, and what makes it classification is that you're asked to take the input, the applicant, and classify the applicant into a set of different classes. In this case, there's the approve or reject class. Okay, and that's easy to sort of encode in the output variable y, which must be either -1 or +1. Okay, so let that be the mathematical definition of classification. The desired output is -1 or +1. Now we can extend this to multi-class classification, where you have more than two classes. Okay, and we'll see an example of that today, actually. Okay. Credit level. So what distinguishes the credit level from classification is you're not asked for a plus or -1 output. The credit level can be any real number. So in this case, the output, so what's different? The output y can be any real number. Okay, and that real number is supposed to correspond to the credit level. Okay, well, we call this type of output regression. Okay, so the first approve or reject problem, we call it a classification problem. When the desired output is a real value, for example, the credit level, we call it a regression problem. Okay, and so what's different between a regression problem and a probability of default? Okay, is that, well, the output here is also a real number, okay, but it turns out that it has to be between 0 and 1 because that's the definition of a probability. So probabilities are between 0 and 1. 0 chances of happening, 100% chance of happening is 1. Okay, so the output, the desired output is a number in the range 0 to 1. So you might think, well, but isn't that just a subcase of regression? Yes, when you look just at the output. But the goal here is that the output should be interpretable as a probability. I'm going to use it as a probability. Probability of a heart attack. Probability of a default. Okay, so unlike a credit level, which is just a number, okay, the probability of default is also a number, but it has a meaning, and you're going to use that meaning in order to do various things later on, to make a decision. So, for example, you've told me the probability they will default, okay, and I'm going to use that somehow to decide what to do with them. Maybe I'll give them credit, maybe I won't, maybe I'll change the credit level, and so on and so forth. Okay, so when the desired output is not just a number between 0 and 1, but it should also be interpreted as a probability, we are going to call this logistic regression. Okay, and so 3 kinds of machine learning problems. We're going to discuss them first in the context of linear models. Okay, and then you might say, well, why linear models? Aren't deep networks and this and that and so on and so forth the in thing for machine learning? Yeah, they may be the in thing, but for example, deep networks at their heart are made up of different components, and each component is sort of cascaded one on top of the other, and those components are linear models. Okay, so it's not that the linear model is not there, it's hidden. We call it a deep network. So in some sense, the linear model that we're going to discuss today, the linear model, okay, it's fundamental. And why is it fundamental? It's fundamental because on its own, it's a very powerful model. And I'm going to argue, I'm going to put my name on the line here, that if you cannot solve a problem more or less with the linear model, then odds are you haven't understood the problem that well. Okay? So I claim that pretty much any problem can be solved with enough thought. You think about the problem, you think about the nature of the task, you think about what are the inputs you're going to get. You should be able to solve it with a linear model. Okay, and we'll discuss exactly what I mean about that in the following lectures. Okay, and so if you can't solve it with a linear model, you haven't thought about this problem enough. Okay, so it's a fundamental model on its own. Okay, and B, it's a fundamental model because it is the building block of other models. For example, deep networks are essentially cascaded linear models. Support vector machines are essentially a more robust version of linear models. Okay, so fundamental model. Okay. On its own, it's a fundamental model and also a building block for other models. Okay. So let us define the linear model first, and then we'll quickly cover classification. Okay, and in the rest of this lecture, we will cover regression and a particular application of regression to classification. And in a future lecture, we will address logistic regression. Okay, so the linear model starts with the linear signal. Okay, so the linear signal. So the linear signal, and let me just state it, and we've already seen it. The linear signal is, let me call it the signal S. Okay, is, you have a weight vector W. So you have W transpose times X. This is the linear signal. Now, remember that both W and X belong to R to the D plus 1. Okay, so W is in R to the D plus 1. And X is in R to the D plus 1. Okay. And why this is the augmented X? Actually, technically speaking, it's in 1 times R to the D. Okay. So it's the augmented X. Okay. Now, why is this called the linear signal? Well, there are 2 reasons why it's called the linear signal, and I'll tell you both of those reasons. Okay. And one of them is actually more important than the other. Okay, so it's linear in X. Okay, so that linearity in X, for example, when we talk about the perceptron, that linearity in X is what results in the separation between the +1 region and the -1 region being a line or a hyperplane. Okay. So this is what gives you the hyperplane. Okay, but look, so linear just means the power, the order of X in this signal is 1. But it's also linear in the weights. So linear in W, the weights. Okay. And that's the type of linear that we are really focusing on when we say linear signal, because this linear in the weights is what makes the algorithms go. Okay. So this is important for algorithms. And so typically when people say, oh, we're talking about the linear model, this is the linear that they're talking about. It's the linearity in the weights, W. In other words, the parameters that we can change in order to pick a final hypothesis affect the linear signal, well, linearly. And that makes the algorithms easy to develop and easy to implement and makes them work. Okay, for example, the perceptron learning algorithm. It's fundamentally reliant on the fact that we are linear in W. Okay. All right. So we have 3 kinds of machine learning problems: classification, regression, logistic regression. They are characterized by the type of the output and more mathematically by the set to which the output belongs. Okay. We're discussing this fundamental model, okay, which is called the linear model. And is it possible to perform all 3 of these tasks using the linear model, whose heart is really the linear signal? So the basic idea is the following. If we want to solve a different kind of machine learning problem, what we're going to do, we're going to take the linear signal and then transform it. Okay? So to solve different types of problem, okay, what do? We take the linear signal and transform it. Okay, and by transforming it in the appropriate way, we can produce an output of the type that we need for the different kind of problem. So we produce an output either y in plus or minus 1, y in the real numbers, or y in the interval 0 to 1. And the transformations are pretty easy. So pictorially, we have the linear signal S, which is W transpose X. Okay, we take it, okay, and depending on the type of problem we like to solve, okay, if we're solving classification, we transform it by just sending it through the sine function. Okay, so we send it through the sine function, which is -1, and then it goes to +1, and the jump is at 0. Okay, so this is the sine function. We send it to the sine function. The output is h of x is equal to sine of W transpose X. Wow, very simple. Okay? And that's exactly what we have been doing so far. And this we call the perceptron. Well, if you transform it essentially using the identity transformation, okay, so the identity transformation, so this is the transformation, S H equals sine of S. This is the transformation H equals S. So it's just the identity transformation. You take the signal and pass it through the identity transformation, you get H of X is equal to W transpose X, and that's a real number. So you don't have to do anything to the linear signal if all you want is a real number. Okay, and this is the linear model for regression. The perceptron is the linear model for classification. Okay, and what about logistic regression? Well, very similar to the sine, except that rather than a transformation that takes you from -1 to +1, we want a transformation that sort of smoothly interpolates. So if this is 0, it smoothly interpolates from 0 to 1. Okay, it does something like that. That's typically called a sigmoid. So we will write that H is equal to some theta of S, where theta is this function. Okay, typically called a sigmoid. So this is typically called a sigmoid. Okay, and so the output H of X is theta of W transpose X equals. Okay, so I just want to show you, okay, without getting into too many details, okay, that with the linear signal as our starting point, we can easily transform the output in order to get the output that's relevant to each of the three kinds of machine learning problems: classification, regression, logistic regression. What we have focused on is classification. So let me just summarize classification, okay? And then we will address some issues with our current PLA, our current perceptron learning algorithm for classification, and then we'll move on to regression today. Okay, so let me erase. We will be back. Okay, so let's quickly summarize the linear model for classification, i.e. the perceptron. But now we have this beautiful theory of generalization, this VC theory, to back us up. Okay, so the linear model for classification. Okay, i.e. the perceptron. Okay, and the hypothesis set H, now I'll call it H sublinear, is hypotheses of the form H of x is equal to sine of W transpose x, where W is in R to the D plus 1. Okay, and D plus 1, remember, because x is this augmented input vector, augmented by 1. Okay, so what is there to say? Well, first, 1. We proved, or you proved in the exercises, and we generally discussed that the linear model, the perceptron in D dimensions, is broken, okay, and has a VC dimension of D plus 1. So the VC dimension, dVC, is equal to D plus 1. Now you might think, well, what does that mean? That immediately places this hypothesis set into the set of good hypothesis sets, the ones with which we can learn, it's feasible to learn. Okay, by establishing the link between E in and E out, at least for large enough n, with high probability. Okay. So we have that E in, E out is linked to E in, and this is for G, okay, plus an error bar, okay, and when you plug in this VC dimension, the error bar has an order of magnitude which is the square root of D log n over n. Okay. This would have been dVC, the VC dimension, but the VC dimension is order of D. So that's nice. Okay, roughly speaking, it says that, if you have a number of data points that's much, much larger than the VC dimension, and typically about 10 times larger suffices in practice, then you've got this link between E in and E out. Fantastic. Okay, so that's the first step of learning. First step of learning accomplished. Check mark. Okay. And, so you're approaching a machine learning problem and you're picking your hypothesis set. So this is the kind of, workflow that you have to implement. You have to check, have I accomplished the first step of learning? In other words, is my error bar between E in and E out small enough? And that depends on the hypothesis set you pick, i.e. its VC dimension, and the number of data points you have. So you can perform this check. Okay? And just because we're doing it with the linear model doesn't mean you cannot do it with any other model, any other hypothesis set for which, somebody else may have done all the hard work and computed the VC dimension for you. Okay. All right. Now, what about the second step of learning? Okay. What about E in? Okay. And that's where we had the perceptron learning algorithm. Remember, we have this perceptron learning algorithm, and we have this theorem: if the data is separable, okay, then you can get E in of G equal to 0. So that's what it means for the data to be separable. Okay, and if the data is separable, you can get E in of G equal to 0, and the perceptron learning algorithm will accomplish this. And perceptron learning algorithm will accomplish this. And you prove this as a theorem. Okay, so that's a theorem. So not only is it possible to get E in of G0, but you can find that hypothesis set from this uncountably large hypothesis set. You can find that final hypothesis that accomplishes the second step. So the second step of learning accomplished. Check mark. Oh, but you're all probably shouting, wait. Okay, a fundamental assumption in this theorem that got E in of G equal to 0 in finite time was that the data is separable. So, immediate questions. What if the data is not separable? What if the data is not separable? Question mark. And, okay, for the general case where the data is not separable, okay, how do you ensure that it's possible to get E in of G close to 0? How do you ensure, quote unquote, E in of G approximately equal to 0? So, two issues we have to address. Now, the first issue, what do you do if the data is not separable? That's very easy for us to address. Okay? And, you basically have to update the perceptron learning algorithm so that it can tolerate error. Okay? And that algorithm we're going to call the pocket algorithm. Okay? And then, how do you ensure E in of G is close to 0? So this algorithm that tolerates error, does it necessarily go to the minimum E in that is available within this hypothesis set? No. Okay, so you might, so how do you ensure E in close to 0? There's an algorithmic side to that. Okay, so the algorithmic side, which is for non-separable data, how do we get to the best hypothesis in this set? It turns out that falls within this class of computational problems which are very, very, very hard. They are what are called NP hard, not only NP hard, but NP hard to approximate. You can't even approximately get to the minimum. So then it turns out that this simple update to the perceptron learning algorithm is quite good. It's almost the best you can do. Okay? But then the issue becomes, well, no, it's not just an algorithmic issue of trying to find the hypothesis in here that has minimum error. There's also sort of this attainability issue. Maybe there is no hypothesis in here with a small enough E in. In other words, maybe this hypothesis set is deficient, in being able to approximate the target function. Okay, and that's where you have to think a little bit. That's where the expert comes in, both the machine learning expert and the expert in the domain. And you've got to think a little bit, how do I solve this problem? And what it ultimately boils down to is you need to pick good features. Okay? And we're going to discuss both of these, today. So, and all kinds of exciting things planned today. We're going to try the projector. We're going to see data. Okay, so the first order of business, turn on the projector. Okay, so here's some non-separable data. Think age, income. The red X's are applicants who defaulted on credit. The blue circles are applicants who paid off their credit. We'd like to separate them with a line. You cannot, because this data is not separable. So here, this blue circle is an error because this line says red. That red X is an error because the line says blue. Okay. Now, PLA. What will PLA do? So let me remind you of the update rule for PLA. It says that you're at some weights W at time T. Find a misclassified point X star, and multiply that by the y in the data, y star, okay, and update the weight to W of T plus W star, or plus Y star X star, and we call this W of T plus Y. Okay, so that's the update rule for the PLA, and at all iterations, you will always have a misclassified point, so it'll go on forever. Okay, so we need to be able to tolerate this error, and the fix is very, very simple. It's what we call the pocket algorithm. And it's so simple, you might think, wow, anyone could have thought of that. Does it really work? And it's pretty much as good as anything. Okay. So first, what's the algorithm? The algorithm is run the PLA. Okay. And, at each step in the PLA algorithm, you take your new weights and you compute E in. You evaluate those weights. Okay. And if the in-sample error for those weights is the best you've seen so far, you put it in your pocket. You store it. You say, that's the best I've seen so far. Now you do the next iteration. You get a new set of weights. Okay, you compute E in for this new set of weights. Okay, compare it with what's in your pocket. If it's better, throw out what's in your pocket and put the new set of weights and keep doing this. So in this way, you are continuously updating the weights that are in your pocket to the weights that achieve the minimum so far. Okay, and that's a reasonably costly process because you have to compute the in-sample error for every new set of weights that you get and then compare that and keep the minimum. Okay. But if you want to be able to tolerate error, well then here's a very simple way to do so. Okay. And it's guaranteed that the weights that are in your pocket can only get better as you do more and more iterations. Okay. So unlike the perceptron learning algorithm, which if the data is separable will stop, the PLA will go on forever because the pocket algorithm will go on forever because PLA goes on forever. So you have to decide when to stop. 10,000 iterations, 1 million, 1 billion, 1 trillion, maybe 1 million, depends on the dimensionality of the data and the size of the data set. Because remember, at each step you perform an update. This takes a running time that's proportional to the dimensionality, and then you have to compute E in, which is a running time that's proportional to the dimensionality times the number of data points. Okay. So computationally, pocket algorithm adds a lot of overhead on PLA, but it allows you to tolerate error. Are there better algorithms? Well, as I mentioned before, finding the hypothesis in this set, i.e. finding the weights which minimize the in-sample error, very hard problem. Computationally hard. We can theoretically formalize that, okay, but let's not. Okay. It just means that it's a very hard problem and people are working all the time. Most of the effort is, we have to run the PLA because the PLA is always improving the weights. Okay? But we can choose where the PLA starts. And if we can improve the starting point, let's say not starting at a random set of weights, but at a set of weights that, is produced by an algorithm that, can be efficiently run and produces a set of weights that are in some sense good, then we start from a good set of weights, and then the pocket algorithm improves those weights. Okay. And so there are methods that improve the starting point based on linear regression, logistic regression, linear blah, 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 blah. We'll see some of these. Okay. So the pocket algorithm is the way to update is the way that we're going to update the perceptron learning algorithm to tolerate error. Okay. That just means we can tolerate error. It doesn't mean that we get to a good E in. So let's talk about how we get to a good E in. How do we get to a good in-sample error? Okay. And, in order to address that, we're going to introduce the data set that we're going to use for the semester. So wow, yay, we're going to see some data today. So let me erase. Okay, so the data set for this class is going to be digits data. And I'm showing you some digits data here, 65473. We have no problem recognizing the digits. Okay. Each digit that we're going to be faced with is a 16 by 16, grayscale image, and you might want the digits. I mean, such a boring solved problem. Yes! Okay. But we need something that's within the scope of this class. Okay. But I'm going to go back to now the very first lecture. Okay. And I said we're going to be discussing the fundamental theory of machine learning, the fundamental algorithms, the fundamental techniques. And so, that means that once you have understood those fundamentals, they can be adapted to solve any problem. Okay, and so you illustrate on this problem, and you'll get familiar with the techniques and the theory. Okay, on this problem, it has all the richness of pretty much any problem, and then you can apply those techniques wherever you want. Okay, so that's sort of the generality of what we have developed so far. Okay, so I'll just mention to you some of the important things that go on when you start approaching the data. Even though I said that the theory that we're going to be developing is not focusing on the data, it's focusing on what you do after you get the data. So here's the data, and you might wonder, well, how did I get this data? It looks so nice. Are digits really that nice? No, and that's because there have been some vision algorithms. So these are purely input pre-processing algorithms that have been run that have nothing to do with the learning. And what they have done, for example, is they have rotated each image so that its axis is vertical. Just a simplification. It's a simple vision algorithm you can run. You will also notice that each digit, in some sense, fills the whole square. Okay, so there's been some rotation applied to make things vertical, and there has been some scaling applied so that the digits each fill the whole square. More precisely, either the length is the height of the box or the width is the width of the box. Okay. and in some cases both. So what this just makes learning later on a little bit easier, because the input examples are all sort of what we call input preprocessed or normalized. Okay. Now, we're not going to discuss such algorithms, but these kinds of considerations are very, very important. Okay? And it's how do you sort of get the data into the form that then becomes suitable for the machine learning. And then once you get the data, that's where the theory that we have developed begins to roll. Okay? So here's an example of the data. Let's get into a little more detail. Okay? So, for example, the 6. Okay, what is it? It contains 256 numbers. So it's a grayscale image. Okay, where -1 is basically white, and +1 is basically black. Okay, so you have 256 pixels, and if you ran a perceptron on these 256 pixels, well, let's see. Okay, the dimension d is equal to 256. Now the augmented vector has 257 dimensions. Okay, and so if you run a linear model with this input, the VC dimension, dVC, is equal to, is d plus 1, so 257. And so the rule of thumb says that you need about, let's say 3,000, 10 times this. Okay, or if you want to be save 100 times this. So let's say you need about, 25K data points to get E in approximately equal to E out. Okay, and we are going to be trying to learn how to classify digits with far fewer than 25,000. Even 10 times that is 2,500. We're going to be trying to learn with 500 data points. So this is just, with 500 data points, you're just not going to have E in close to E out. So that's a disaster. Okay? So when we approach this problem, we have to say, well, we have 500 data points. So what kind of VC dimension can we deal with? We can deal with a VC dimension of about 5, of that order. So we want dVC approximately 5 or less. 5 or less. Okay, in order to solve this problem. Because we need to establish the first step of learning. First step of learning. Okay, now, how are we going to accomplish that and simultaneously be able to get E in close to 0? And that's where what I'm going to discuss now is so fundamental, so absolutely important. It's this notion of features or feature construction. So feature construction. Okay, or how to get E in approximately 0 with such a small dVC. Okay? And if you look at the dictionary definition of the word feature, it's sort of something conspicuous, something that's distinctive, something that identifies an object. Okay? And so when you think about the digit classification task, and now this is before you look at data. Let me emphasize, we are doing all this stuff before we look at data. You understand, now I'm going to just illustrate by showing you on the data, but all of what I'm saying has to be done before you look at the data. So, for example, the top left pixel is white, and it's going to be white for pretty much any digit. So, putting it in as a dimension on which you're going to build your machine learning model, it's just a dimension that doesn't vary, but it's going to affect your input dimension and your VC dimension, and then your error bar, and it's going to lead you to conclude that you didn't learn. Okay? So, there's a lot of redundant information in the data, but there's also a lot of useless information in the data. Okay? And so what we can do is we can try to summarize the input in terms of features that are going to be useful for classifying the digits. Okay? So summarize the input into features that are useful for classifying digits. Now I want to emphasize that this does two things. What are the two things it does? The first thing it does is it can reduce the dimension significantly. So it will reduce dVC for the linear model significantly, which means that we will get control of the error bar. So that's the first thing it does. And then you might wonder, but well, then we might, affect our ability to get E in small, and that's where we highlight the word useful. Okay, and so this is where you sit down with the digits expert or the medical expert, and you sit down and say, okay, great. Now you are collecting this kind of data. Now, what are the features that are going to be useful? Okay, and so you think about this problem in some abstract sense, and you try to figure it out. Okay, and you sit down and try to figure it out. Okay, and in doing this, you are increasing the chances. You're embedding into the feature only what is important. Okay, and that's a hard task. Okay, but that's the task you have to do to solve a machine learning problem well. You have to think about what are the characteristics of the input that I need. And they may be measured, they may not be measured. You can tell your client, maybe go and measure those things. Okay? And when you do that, you will find that once you have constructed the right features, the linear model will solve your problem beautifully, because the linear model comes along and controls E in versus E out. Okay? And that's what I meant when I said that if you cannot solve the problem with a linear model, you haven't thought about the problem. And any problem can be solved with the linear model as long as you think about the problem and think about what are the right features. So, for the digits, let's think about what are the right features. Okay, so now we're not looking at the data. So I'm closing my eyes. I'm not looking at the data. Okay, and I'm thinking, well, my task is to, let's say, classify a 1 from, let's say, a 0 or an 8, or let's say a 5. Okay. And if you think about this problem, now look, this is not data. I've just drawn this. Remember, my eyes are closed. Okay. And so I'm looking at this and I'm saying, well, the 1 has a few black pixels. So you could add up the number of black pixels. Okay. Let's call that intensity. Okay. And the 5 certainly has more black pixels. Okay, so this will have a high intensity, this will have a low intensity. So I expect intensity to be a good way to distinguish certain digits written down from others. Now, this is just from my knowledge of the problem, not from my knowledge of the data. Okay, that's key. Okay. What's another distinguishing feature? Some kind of symmetry. Okay. So think about it. Well, if I rotate the 1, it comes back to itself. Okay. Whereas the 5, if I rotate it, it's totally different. Okay. So, and think about other digits like the 0. Oh, lots of symmetry. You can rotate even a quarter turn, and it'll more or less be itself. Okay, so symmetry. Okay, so now I'm thinking about features, and let's stop there. You can come up with your own features, and in fact, on one of the assignments, you will be asked to come up with your own features. Okay, but all I'm doing here is thinking about what I know about this problem and what features would likely be able to distinguish between the two in the various different classes. Okay. So this is the first step, and now I need to convert these definitions of features into mathematical definitions. Okay, and then I need to be able to implement those in some kind of an algorithm, some kind of a program that takes an input and immediately converts it into these two, let's say, features. Okay, and basically what I'm going to do is I'm going to transform my data from this 256-dimensional data into, let's say, 2-dimensional data, okay, where my 2 dimensions capture intensity and symmetry. Okay. So this takes my data from 256 down to 2 dimensions. But look, the VC dimension is just now 3. DVC is equal to 3. So, because I'm using the linear model, and that's why the linear model is so powerful, it automatically takes care of the first step, providing you have a small dimension. And now you need to take care of the second step by thinking about what are the right features. Okay. So, let me show you this data. Okay. But instead of the 256 dimensions of, grayscale values, which, don't really make sense to a human from the perspective of separating out, from the perspective of distinguishing digits. Here are the data now plotted, just like age and income, but now I have intensity and symmetry. Beautiful now. You see, if I put a line somewhere like this, or maybe like that, there are many ways now to separate this problem. I'm showing the digits 1 versus 5. So imagine that we simplified our task to only distinguish between 1s and 5s for the moment. Because there's this famous mathematician who said, you're approaching a problem. It's a difficult problem. Okay. The odds are, if you've come to a difficult problem that you cannot solve, the odds are there's a simpler problem you cannot solve. Okay. So let's try to solve simple problems. Okay. Because we have no hope at difficult problems otherwise. Okay. So look at this. The 1s have low intensity, high symmetry. Now we're looking at the data. You're not allowed to do this. Because I'm trying to teach you what's going on. So I have to show you the data. But in practice, you can't look at the data. I just want to show you that when we went into these two features, look how beautiful it is. And you could separate with a line. Okay? The linear model solves this problem almost beautifully. Okay? You don't need sophisticated this and that and this and that if you sat down and thought about the features. Okay? Now I want to show you something else about data. And, if you think you're ever going to get data that's perfect and clean, think again. So let me show you some things in this data, and you might wonder, what? So, the line would almost get this perfect, except for some strange data point. So there's this guy here, okay, this blue circle here, which seems to have a high intensity, not much symmetry. Well, when you actually look at that data point, it's this one. You look at it and say, yeah, some people write ones like that. Most of the ones are nice and symmetric and not many black pixels. But some people choose to write their ones with this very fancy, big, asymmetric one. You should be taught in high school that you're not allowed to write ones like that, because didn't you know we're going to try to build a machine learning algorithm to distinguish ones from fives? Okay. And then what's this? Well, it's classified as a 5. Okay. It's right over here. You're wondering, what is this thing that's a 5 with almost no intensity and a huge amount of symmetry? Now you might wonder, how am I measuring intensity and symmetry? Well, you have to come up with your own mathematical definitions. I came up with my own. You can come up with them. Figure out how to measure, intensity and symmetry. Intensity is easy. Just effectively count the number of black pixels. Symmetry is a little bit trickier. You have to come up with an algorithm to measure symmetry. And this thing is very symmetric, but it's a 5. I don't know who writes a 5 like that. Not me. Okay. But that's the data. You can't argue with the data. The data says that's a 5, and that's going to cause problems for machine learning. And you might think, you can now try to think to yourself, what if I used the most complicated model on the world and tried to make it so that were indeed classified as a 5? You'd have to contort and do this and that and so on and so forth. Okay, so you might think, what would happen there? Okay, but this is the data in my intensity symmetry features, and you see that data comes in all shapes and forms, and we have to be ready to deal with this, okay, in some sense. And, we are now ready to run our perceptron learning algorithm. So we have data in 2 dimensions. Let's run the perceptron learning algorithm and see what happens. Okay. It produces this classifier, which is okay. That's what it produced. Okay. That's what it produced after 1,000 iterations. It doesn't look that good. Okay. Okay, and what I'm showing here is, as you run the perceptron learning algorithm, the blue curve here is the in-sample error you observe. Okay, wild. And that's because the data is not separable. Whenever the data is not separable, the perceptron learning algorithm behaves very erratically. So you might think, imagine if I had stopped at 250 iterations, I would have got a beautiful in-sample error. Okay, but if I had stopped at 700 and let's say 705, I would get a bad in-sample error. And I happened to stop at 1,000, and my in-sample error wasn't that great. Okay, that's the problem with the perceptron learning algorithm. Let's see what happens. Okay, now, one thing I want to point out. What is this red curve that's bouncing up and down, bouncing up and down, bouncing up and down? Okay, that's the out-of-sample error. You might think, how did I measure that? Well, we have our tricks. And what's going on here is I'm going to give you 500 data points to learn with, and we're going to keep a data set of size 10,000 or so, 5,000 or so. Think of those as 5,000 test points, which you will be tested on. Okay? So it's a measure of the out-of-sample error. I care about your performance on those test points. Okay? Look at how it's going up and down, also wild. But that's not the important point. Okay? The important point is, look at how it goes up and down, up and down, up and down, up and down, nearly perfectly in sync with the blue E-in curve. And I'm going to ask you to pause the video and think about why. Why does the red curve go up and down almost perfectly in sync with the blue curve? Okay. So pause the video. And if you're coming back and you figured it out, great. Okay, you really understood the theory. Otherwise, if you're just here for the ride, that's the theory at work. Okay, because we have just 2 dimensions, so the VC dimension is 3, and you got this tight link between E-in and E-out. That's the theory at work. That's why we do theory, because it works for us. Okay? So what this means is that your out-of-sample error will mimic what you see in sample. It'll go up and down according to, according to the in-sample error. In other words, when you find a small in-sample error, it'll tell you that you have found a small out-of-sample error. This is, in some sense, the error bar. Okay, this height here, and then as E in goes up and down, E out goes up and down. That's the link that we worked so hard to establish theoretically. Okay, but this erratic behavior is because we're running the PLA. If we run the pocket algorithm, it very quickly comes to the minimum here and stays there. And look, it's a much better classifier. Okay, this guy's up here, this guy's down here. Okay, you might think, well, maybe I can tilt it a little, and probably if you ran for another 1,000,000 iterations, this is just 1,000 iterations, you'll probably do much better. Okay, so the difference between PLA and pocket. Okay. Let's talk about linear regression. So let me erase. Linear regression. Okay. So, example. Your applicant for credit arrives with their attributes, and in the classification task, we must approve or deny. In the regression task, we have to give a credit line, a dollar amount, a real number. And remember, we discussed the transformation. The only difference now to make the linear model, the linear signal, give us a real output, a real number, a credit limit, a credit line, okay, is to not apply the sign. So the hypothesis h of x is just W transpose x. Okay. Now let me show you in a picture what we're trying to do. So it's easier. So I'm showing you the two-dimensional version. Here's the one-dimensional version. Okay, so you have an input x. You're going to multiply by, you're going to add the augmented 1, and you're going to do W0 times 1 plus W1 times x. Okay, so that's what this line looks like. There's a slope and an intercept. You have two ways you get to pick. And then you observe the y values. Okay, and you would like to pick the line to fit the y values. And, because the target function has noise, in general, you will not be able to fit the y values, so you make these red errors. Okay. Now, in more than one dimension, you're not fitting with a line, you're fitting with a hyperplane, but the same idea, you make errors on your data. Okay? And so we can define an in-sample error, okay, which is the sum of the squared errors. This is a standard in-sample error for regression, and we can define the out-of-sample error, which is the expected squared error. Okay? And just like with classification, we're going to approach this problem in two steps. Okay? The first step is, how do we get the smallest possible in-sample error? Can we find the set of weights with the smallest possible in-sample error? I.e., can we find the weights that minimize this mean squared error? This is sometimes called the mean squared error. Okay. And then, okay, it's beyond the scope of this discussion, but I'll just show you that, for the linear modeling regression, you do get the link between E in and E out, depending on the sort of statistical model that you assume for the errors. And we won't go into that, because our main focus is classification, but I feel like I need to give you some regression knowledge as well. Okay? So, what we're going to do is we're going to mostly focus on how do we get the hypothesis, the weights W that minimize this error. So that solves the second step of learning. How do we get small in-sample error? Okay, and you'll find a weight that minimize the in-sample error, and you look at it, and that minimum in-sample error will be small if you chose good features. If you chose bad features, we don't know. Okay? But there's still this algorithmic task that we're going to solve. So let me turn off the projector, and let's derive the algorithm that minimizes the in-sample error for regression. And we're going to do it on the board, and it's going to use a lot of matrix analysis. Okay, so let me switch off the projector. I'll be back. Okay, so let's talk about linear regression. Okay, and your mental picture should be, in one dimension you have x and y. Okay, and you have data points, and you try to fit with a line or a hyperplane. So our discussion is going to be completely general, d dimensions. Okay, and the in-sample error. So your hypothesis h of x is W transpose x. Okay, and the in-sample error E in of of what? What does the in-sample error depend on? It depends on your data and your weights, but the data is fixed, so it effectively only depends on your weights. So E in of W is equal to 1 over n, the sum from I equals 1 to n of h of xi minus yi squared. Okay, so the in-sample error is the mean squared error, and since this is what h is, so this is 1 over n. Okay, the sum from I equals 1 to n of w transpose xi minus yi. So let me call this the prediction, the in-sample prediction for data point xi. Okay, and so let me define yi hat is equal to w transpose xi. Okay, then this is equal to 1 over n, the sum from I equals 1 to big N of yi hat minus I forgot the square, minus yi squared. Okay, so this is the mean squared error, standard regression error, where you have your prediction, what you're trying to accomplish. You take the difference, square it, and you add them up and take the average. Now, squaring has the convenient property of no matter whether your prediction either underpredicts or overpredicts, this is an error that's always positive. So that's one nice convenient thing. There are many errors that one could choose to define as your error. And remember, we talked about error and error metrics and risk matrices. It's really up to the user to define the error metric, and this is a particularly convenient error metric. Okay, you can think of this as we're trying to find the weights W so that the predictions are approximately equal to the yi's. So we're trying to get yi hat, the predictions approximately equal to yi. Whereas in classification, we only care about the sign of yi hat approximately equal to the yi, which was plus or minus 1. So that's the fundamental difference between the algorithm that tries to minimize the errors, is that we are trying to actually approximate the values now, not just the sign. Okay. It's particularly convenient to go into sort of a nice matrix notation. So with that in mind, let me define a vector y. Let's define y as the vector that contains all the target values in the data, y1, y2, y3, up to yn. So this is the target vector. Now remember, what's our goal? Our goal is to find the weights W that minimizes this error. Okay. So I'm defining a target vector, and along with that I can define the prediction vector. So let me define y hat is, what are the predictions of a particular hypothesis. So this is y1 hat, y2 hat, and y3 hat, and so on, yn hat. Okay. Similarly, I can construct a matrix that has all the data points. This is sometimes called the data matrix. So this is the prediction vector. And let me define the data matrix X. Okay. Now, what is X? So remember, each data point is a d-dimensional vector, but d plus 1 when you augment with a 1. So X is going to have rows which are my data vectors, my input vectors for each data point, for each example. Okay. So I'll define it as the rows. Okay. So there's a 1. Okay, and then there's x1. Now technically, because x1 is a vector, okay, x1 is a d-dimensional vector, if I want it to be a row, I have to take the transpose. So x1 transpose, and that's a vector like this. Then y1, that's the augmented. Then x2 transpose like that. So that's what the data matrix looks like. But since we defined the augmented augmented vector to already contain this one, I just wanted to remind you that that one was there. But we already just defined the vector to contain that one. And so this is just x1, the augmented vector transpose, x2, the augmented vector transpose, x3, the augmented vector transpose. And so xn, the augmented vector transpose. Okay, so this is the data matrix with rows as augmented. And I'm just reminding you, okay, even though we already said that, always assume that your vector x has now been augmented with this one, with augmented input vectors okay, with rows as augmented input vectors, so with rows. Okay, so that's the data matrix. Okay, so now what I want to observe here is that this is a sum of squared differences. Okay, and if you look at this vector and this vector, if you take the difference, you get the differences. So the norm squared of this difference is exactly the sum, the Euclidean norm squared is exactly the sum of these differences squared, the sum of these squared differences. So this here is exactly 1 over n times the norm of y hat minus y squared. Very nice. Okay, very nice. It's a very compact way of representing the in-sample error, linear algebraically. And that's one of the reasons why it's very convenient to go into linear algebra notation. Okay, and now let me remind you that what is y1? So for example, y1 is equal to w transpose x1. Okay, that's the linear model. Okay, sorry, y1 hat. y1 hat. It's w transpose x1. Okay. But lo and behold, that's exactly equal to x1 transpose w. Okay, that's the beauty of the inner product. Okay, doesn't matter. You can transpose an inner product. This is just a number, so this is the transpose of that number. y2 hat is equal to w transpose x2, which is equal to x2 transpose w. Okay, okay, now let's come, and so on for yn hat is equal to w transpose xn, which is equal to xn transpose w. Okay. So x1 transpose w is this is a row x1 transpose times w, which is a column. This is a row x2 transpose times w. This is a row, then you'll get the row x3 transpose times w times the column w, and so on. You've got the row xn transpose times w. But look, this is exactly the data matrix. This is big X, what we defined as the data matrix. So the vector y, y hat, is exactly equal to x w. Oh, so nice and beautiful and compact. Okay, so let me erase this little bit of justification for that. Now, of course, you can go and verify this linear algebraically. And I leave that as a task. This heuristic visual derivation is exactly the derivation of that. So what that means is that I can replace here with 1 over n, the norm of x w minus y squared. Okay. And now I will remind you, okay, so let's summarize. Okay, let's summarize. En of w. So En of w is 1 over n, the norm of xw minus y squared. We've derived that. Okay, linear algebraic notation for the in-sample error. Wonderful. Very convenient. Okay, because, let me remind you again, that the norm of any vector a, let's call it z, the norm of a vector squared is exactly z transpose z. Okay. So the norm of this guy squared, this is equal to 1 over n xw minus y transpose xw minus y. So it's a transpose, this is a vector, so this vector transpose times itself. Okay, and so this is 1 over n w transpose xw, okay, minus y transpose xw minus y transpose xw. Sorry, this is the data matrix big X. Okay, minus w transpose x transpose y minus w transpose x transpose y, and then plus y transpose y, plus y transpose y. Okay, this is the in-sample error. Okay, and this is a number. Since this is a number, this number equals that number. So this is equal to 1 over n times w transpose xw minus twice w transpose x transpose y, because this and this are the same because they're both numbers, and this is the transpose of that, and the transpose of a number is just the same number, okay, plus y transpose y. Okay, so this is the in-sample error. Now remember, what was our goal? Let me remind you what our goal was. Our goal was to find the set of weights that minimize the in-sample error. Okay, for regression. This is for regression. Okay. And so here we have the in-sample error represented as a function of the number of the weight vector. Okay, now let me remind you that the data matrix X and the target vector Y are fixed. We don't get to change them. The only thing we get to change to minimize the in-sample error are the weights. Okay? And, straightforward calculus tells us that if you want to minimize a function of some variables, you take the derivative and set it to 0. Okay, so take the derivative, of E in of W and set to 0. Okay. So now I want to remind you that this is, okay, so in one dimension, think of a function f of W equals to AW squared plus BW plus C. If it was a one-dimensional function, no problem. df by dW equals, 2AW plus B. Okay, and you set this to 0. This implies that W equals minus B over 2A. No problem. Okay. This is one single variable calculus, no problem if this W is a one-dimensional quantity. Okay, but here it's complicated by the fact that W is a vector, so we have to use vector calculus. So the derivative is really we have to set the gradient. We have to set the gradient of E in of W to 0. Okay, but this is still a quadratic. You can think of this as the equivalent of A in that one-dimensional version, and you can think of this as the equivalent of B. Okay, and then this as the equivalent of C. Okay, and so when you take the gradient, the process is very similar. Now I'm going to leave this for you to verify. The gradient of E in of W is exactly 1 over n. Okay, now remember what we had before. We had 2AW. Okay, we had 2AW. So we're going to have 2, A is X transpose X. We're going to have 2 X transpose X W. Okay, and then we had, plus B. But in our case, the B is minus 2 X transpose Y. So we have minus 2 X transpose Y. Okay, so this is the gradient of that. And you might wonder, what? We can just take that over from the one-dimensional world? No. I'm asking you to verify using your vector calculus knowledge that the gradient of this E in is exactly this expression. Okay, and so you have to use vector calculus to do this. I'm just showing you by analogy that it's very similar to what happens in one dimension, but you have to derive this. Okay, and what we have to do is set this equal to 0. So this means that this term has to be 0, and the 2's cancel. So this means that we need to set X transpose XW equal to X transpose Y. Okay, we have to pick W so that this equality holds. Then we know we're at the minimum. These equations, this is a vector equation. These are sometimes called the normal equations. So there, I've derived for you the normal equations. Okay, and when the matrix X transpose X is invertible, we can just multiply both sides by the inverse, and we get that W star, or we can call it W lin, or W star, whatever you wish. W lin is equal to, we pre-multiply both sides by the inverse X transpose X, inverse times X transpose Y, we get X transpose X, inverse X transpose Y. Solution when X transpose X is invertible. Now it's possible, though rare, that X transpose X is not invertible, in which case you have to use what's called the pseudo-inverse. We use the pseudo-inverse here. So let's not get into those technical details. The point is, and this is the important point, for regression, we have an exact formula for finding the best weights. The best weights that get, h of xi approximately equal to yi on the data, for fitting the data. Okay. So you can think of this as a single-step algorithm. So as opposed to the PLA, which is, an iterative algorithm. It updates the weights one by one. Okay. Now, I want to emphasize that the PLA, which updates the weights one by one, looks like it's gradually learning. Because the weights improve and the line gets better and better. It looks like it's learning. Okay. Whereas, we can call this the pseudo-inverse algorithm. There's one-step algorithm for linear regression. Where's the learning? There's no learning here. You just, boom, go to the optimal weights. Bam, you're done. Okay. So let me emphasize Okay, that the PLA, which one step at a time, seems to get better and better on the in-sample error, is not learning. That's just fitting the in-sample error. And just because you do that gradually and things look better gradually, it gives you the feeling that you're learning. I don't care about your feelings. The learning doesn't care about your feelings. Okay? That it feels like learning. No, that's not learning. Okay? The learning comes when at the end of the day, you produce your final hypothesis. So this is my final hypothesis, G. And at the end of the day, the PLA produces the final hypothesis. So it's only at the end of that iterative process you produce the final hypothesis. And then we say, does it approximate F? That's when we say you have learned. So just because it doesn't look like there's an iterative learning here, this is still learning as long as this final hypothesis does well on a test point. You have learned. Although you haven't incrementally optimized your fit to the data. But that's not learning. That's just incrementally optimizing your fit to the data. Okay, so let me summarize the pseudo-inverse algorithm for regression. So summary. Let's do it here. Pseudo-inverse algorithm for regression. Okay, so step one, put your data into a matrix form. So put your data into matrix form. So you collect all your y values into the target vector. Okay, and you collect all your x vectors, your input vectors into your data matrix. X1 transpose, X2 transpose, okay, all the way to Xn transpose. And I just want to emphasize, and I keep emphasizing this, there's the augmented one in here. Okay? Very important. If you don't put the augmented one in here, you will not pull out the intercept of your fit. Okay. And then, apply the pseudo-inverse algorithm. Apply the pseudo-inverse algorithm. So W lin is equal to X pseudo-inverse Y, okay, where X pseudo-inverse is equal to X transpose X times X transpose X inverse times X transpose when X transpose X inverse exists. Okay. And 3, your final hypothesis G of X is equal to W lin transpose X. That's it. Bam! One step learning. Beautiful! Okay, and what does this accomplish? This accomplishes that G of Xi for each data point is approximately going to equal Yi. That's the goal in regression. You are trying to approximate the actual values. In classification, all you care about is that the sign of this guy matches the actual values. Okay? And this is just, let me mention. Okay, so you might wonder, well, how the heck do I compute this? Well, you compute a matrix, then you invert it. Okay, computing this matrix is if the data is of, if you have n data points and d dimensions, computing this guy is an order of nd squared algorithm. So this is, the running time here is order of nd squared plus d cubed, where d is the dimensionality and n is the number of data points. And, if n is huge, 1,000,000, and d is huge, 1,000,000, well, then this is 10 to the 18. So even though it's one step, it could be one very expensive step. And sometimes, for such huge data sets, we can develop iterative versions of this, and we'll talk about that later. Okay. But for the moment, the pseudo-inverse algorithm gets you the exact optimal in-sample error. Okay. And the weights that correspond to that optimal fit in-sample. What about the step 1 of learning? Well, we're not going to get into too much depth. The statisticians have really, hammered this thing, and they, based on various kinds of assumptions, okay, but ultimately it all boils down to the fact that the linear model is good. Okay, so just like we can control E in versus E out for the linear model in classification, i.e. the perceptron, E in, E out is of G is equal to E in of G plus order of D over N. Okay, so just like the VC dimension, and i.e. the dimension entered for classification, it also arises in regression to control the link between E in and E out. The point is that for the linear model, you get a good control between E in and E out. Okay, and I won't get into too many details. I just want to mention one more thing, and then we'll wrap up. We'll close for the day. Okay. Classification. So the pocket algorithm. Okay, and in general classification, it's hard to minimize E in. Okay, and the pocket algorithm is one attempt. And I mentioned before that the starting point, if you can improve the starting point, then the pocket algorithm might be able to further improve you. And okay, so that's a way to improve the pocket algorithm. Okay, and now we are presented with a very interesting algorithm. The pseudo-inverse one-step algorithm gives us a set of weights. It gives us a set of weights, W lin, where, so this comes from the pseudo-inverse algorithm. Okay, and let's look at the pseudo-inverse algorithm, and it runs no matter what y values you give me. So let's consider a classification problem where the y values happen to be plus or minus 1. Okay, so if the y values happen to be plus or minus 1, i.e. you are in the classification realm, you can still run the regression algorithm and produce a set of weights. So you can still run the pseudo-inverse algorithm and produce, W lin. And what will it accomplish? It will accomplish W lin transpose xi is approximately equal to yi. But if this is true, if the actual values are approximately equal to the yi, well then the sign will typically agree. The sign of these will typically, if the actual value is close to the plus or minus 1, then its sign will also be close to the plus or minus 1. Okay? And so what that means is that the regression weights will usually perform quite well even for the classification task itself. So regression weights are usually quite good at classification. But that leads to a nice idea. Why don't, when you're faced with a classification problem, first run this beautiful, one-step algorithm to get the regression weights. And who cares that the y values are all accidentally plus or minus 1? You still get a set of weights. You can use those weights as the starting weights in the pocket algorithm, which then can further improve, and it'll further improve for classification. Okay? And so we call that regression for classification. So this algorithm we call regression for classification. So the final output is still going to be sine of this. Okay, but you use the linear regression weights as the starting point to run the PLA or the pocket algorithm. And that works quite well in practice. It's very hard to beat. So now, simultaneously today, we have discussed, the way to tolerate, non-separable data with the perceptron and the perceptron learning algorithm, which led to the PLA, which led to pocket, which then led to regression for classification. So start with regression, okay, and then use those weights in the pocket. Okay. We then discussed regression, where the task is to approximate the y values in the data, not just the signs, to approximate the y values in the data. Okay. And then boom, we have this beautiful pseudo-inverse algorithm that exactly minimizes the error. Okay. And with that, we're going to sign off. See you next time.